Hello and welcome to this video. In this video, we are going to talk about uncertainties. And as usual, I'm going to use questions in order to reinforce the concept or to remind you about the concept. Let me start by stating that there are three levels of uncertainties: absolute uncertainties, fractional uncertainties, and percentage uncertainties. And each one of these levels is used depending on the kind of operation that you get in the equation. What do I mean by that? If the equation has got addition or subtraction, maybe you may be adding two physical quantities which must be of the same type, like V is equals to U plus AT, or you are finding the difference between two physical quantities, that is, there is a subtraction somewhere. Then the level of uncertainties that you should use in that operation in order to get the uncertainty in the final answer when you add or subtract should involve absolute uncertainties. But when you are dividing two or more physical quantities, or you are multiplying two or more physical quantities, then the level of uncertainties that you should use is either fractional or percentage. And each one of the examples that I'm going to use here reinforces each one of those concepts. And let's go to the first example so that we can see how we use one of these levels. Now, in this question, it is in May-June 2002, question 5, we are told that the power loss P in a resistor is calculated using the formula P is equals to V squared over R. So you can see here there is a multiplication of two physical quantities. They are of the same type, they may be different, and there is also division. The uncertainty in the potential difference is 3%, and the uncertainty in the resistance R is 2%. What is the uncertainty in P? So this is how we are going to proceed. We look at the equation and we decide, since there is no addition here, then we are going to involve either fractional uncertainties or percentage uncertainties. And because we've been given percentage uncertainties, that is what we might want to get. But you must realize that the percentage uncertainty, for example, the percentage uncertainty in P is obtained by multiplying the fractional uncertainty in P by 100. That is how you end up getting the percentage uncertainty in P. It should be given by the percentage uncertainty in V this percentage uncertainty in V plus another percentage uncertainty in V, which is similar to this. And instead of writing another expression like this, I'll just put 2 here. But since you may be encountering this for the first time, let me just write it down so that we can draw a certain conclusion. Then plus the percentage uncertainty in R. So that is what happens. So when we want to get either the fractional uncertainty in our answer, or absolute uncertainty in our answer, or percentage uncertainty in our answer, we add. We always add. It does not matter whether the expression had addition or subtraction. When we want to get the absolute uncertainty in our answer, then we add the absolute uncertainties or the various physical quantities that we are using. Here we are multiplying and dividing. Again, it does not matter whether it's multiplication or division, we add either their fractional uncertainties or their percentage uncertainties. Observe that. Then the V is multiplied by itself twice. So instead of writing this one separate from this one, I would just have written 2 times this percentage uncertainty here. This power could be maybe 3/2. It is the same power that I would use here. So let's proceed with this, because what we want is the percentage uncertainty in P. So we are going to get 2 times the percentage uncertainty in V, which is 3% plus 2%. And this being 6 plus 2, we get 8%. And that is how the answer becomes C. Let's look at the next example, because it may be giving us a different way of working with these uncertainties. And this example is found in the May-June 2003 paper, question 2. And this is the way it looks like. Let's see what we have. A student makes measurements from which she calculates the speed of sound as 327.66 meters per second. She estimates that her result is accurate to 3%. Which of the following gives her result expressed to the appropriate number of significant figures? Now, this question is important in 2 ways. The physical quantity that is given, the uncertainty in this physical quantity is percentage. But now they want us to use that to know how this value should have been written. And this is usually very common in examinations, whereby you work out your uncertainty, and then it should dictate how you should write your final answer. And this is what we are talking about. So this one is speed. It is V. It is this much. So if we get the absolute uncertainty in the speed, divide by V, which is fractional, of course we multiply by 100, we are going to get 3. That is what it tells us. We must get the absolute uncertainty, because the absolute uncertainty is the one which dictates the way we should write this V. It tells us how many number of significant figures we are going to use. So let's substitute here and see what we get. We've got 100 times delta V over the value of V is 327.66. This should give us 3. And we can get now delta V as 3 times 327.66. All that we divide by 100. Let's see what we get when we calculate this. So I have 3 times 327.66, and I divide that one by 100, and I'm going to get 9.8298. 9.8298, and it should have the units of speed. Now, the point I'm emphasizing in this question is this: uncertainties are usually written to one significant figure, because if we are uncertain about 9, 8 is not worth writing down. We're even more uncertain about 8 or 2 or 9 or 8. So it's important to realize this, that this one will be 10 meters per second. So we round up to this value, but this value again gives us a value with 2 digits. But before we can know how to write down this value, let's appreciate that this 10 is going to affect 2 and 7 here. 2 and 7, it will affect this. So it will be like 327.66 plus or minus 10 meters per second. Let me write that one down because we need to discuss and agree on a few things here. 327.66 plus or minus 10. So this will be, since this value affects these 2 digits here, these are not worth writing down. So I round it up to 328. 328 plus or minus 10. Again, meters per second. This digit here has got 2 significant figures. So it is not clear whether it is to 2 significant figures or 1 significant figure. We need to make it to be to 1 significant figure. So this one is going to be 32.8 plus or minus 1, because this one here affects this digit here. That digit. That one affects that one. This is by 10 raised to 1, which we hardly write down, meters per second. So, since this one affects this digit, 8 is hardly worth writing down. So, we're going to round it up, and it becomes 33 plus or minus 1, all these by 10 raised to power 1 meters per second. So, point number 1, uncertainties, especially absolute uncertainties, they usually express to 1 significant figure. Once you do that, then check the value in your calculated value that is affected by that digit. Any other digit after that figure, after that digit, is insignificant and it is not worth writing down. So you round up your value to be this. So if now I open this, it will be 330 plus or minus 10 meters per second. And that is how our answer becomes C. You can see how close it was. So if you don't know these rules, you can easily get confused. Just remember this. Uncertainties are usually expressed to 1 significant figure, unless they are deliberately given in a question. If they are deliberately given in a question, then use them the way they are. But if you've got the freedom to write it down all by yourself, then always try to write the uncertainties to 1 significant figure, and you can use standard form to do that. When you write the uncertainty as 10 meters per second, this number, somebody looking at this number may not know to how many number of significant figures you have rounded it up to. But when it is written in standard form, it's clear whether it is 1 significant figure or 2 significant figures. Now let's look at the next example. The next example comes from October-November 2003, question 5. And here we have it. What are we given here? We are told that a thermometer can be read to an accuracy of 0.5 degrees Celsius, plus or minus 0.5 degrees Celsius. The thermometer is used to measure temperature rise from 40 to 100 degrees Celsius, and we are required to calculate the percentage uncertainty in the measurement of the temperature rise. So you can say this one is theta 1, this one is theta 2. We want the temperature rise, which we are just going to call theta. Theta is going to be equal to theta 2 minus theta 1. Now, their percentage uncertainty is given here, so definitely we will need to see that our expression here involves subtraction. And remember what we agreed at the beginning of this video. When we add or subtract physical quantities, which obviously must be the same, like for example, theta 1 and theta 2, they are the same type of physical quantities. How do we deal with the uncertainties? We just need to add the absolute uncertainty. So over here, we are going to find that the absolute uncertainty in theta, for example, theta 2 minus theta 1 will be 100 minus 40. And this will be 60 degrees Celsius. So we can say theta, which is the change in temperature, is going to be equal to 60 plus or minus, you see each one of them had this absolute uncertainty. So we add 0.5 plus another 0.5, we get 1 degree Celsius. So we want to get the percentage uncertainty in that temperature rise. So it will be delta theta, that is the absolute uncertainty in theta, divided by theta itself times 100. This is how we express the percentage uncertainty in the temperature rise, which will be a delta theta, which is 1, divided by theta itself, which is 60, times 100. Let's see what that gives us. So we have 100 divided by 60, and you get 1.666, approximately 7 cents, like that. Now, here, if we were working out this question in paper 2, and the question did not ask us to show that the percentage uncertainty is this much, and we are just required to write our answer, this is what we would do. We would go ahead and write this as 2%. 2% to avoid the idea of having two digits here. So especially when it is absolute uncertainty, we avoid using two significant figures. But in this case, we've got no otherwise other than check what the examiner has given us, and you can see the closest answer is that one. This type of question, you can see it forces us to move from absolute uncertainty to fractional uncertainty all the way to percentage uncertainty. Just follow the rules. Always ask yourself, when do you use absolute uncertainty? When do you use percentage or fractional uncertainty? It's important to do that. Let's look at the next example because it's going to give us more practice with uncertainties. And this one comes in the May-June 2004 paper, question 5. Let's see what we have. You can see it combines absolute uncertainty with percentage uncertainties. So let's see what the question is asking us to calculate. In a simple electric circuit, the current in a resistor is measured to be this much. Is the current and its absolute uncertainty. The resistor is marked as having a value of 4.7 plus or minus 2%. So the resistance, the uncertainty in the resistor, it's not absolute, but percentage. If these values are used to calculate the power in the resistor, how do we calculate power when we are given current and resistance? The best equation to use is I squared R. And you can see here we are involving multiplication. It is the first example we looked at, where we were just dealing with multiplication. So let's go ahead and see how we deal with this one too. So we want the percentage uncertainty in the power obtained. So the percentage uncertainty, which is written like that, is going to be equal to the percentage uncertainty in the current and because of this square we multiply that by 2 plus the percentage uncertainty in R. Let's go ahead. There is 100. Absolute uncertainty is this much here, 0.05 over 2.50. All that multiplied by 2. And when we come here, we have 4.7 plus or minus 2%. So that one is already a percentage. So we just need to use 2. Because it is the value of the percentage uncertainty in the power that we want. It is not, we are not interested in the power itself. In the calculation, you can see that. So let's see what we get. So 100 times 0.05, that just gives us 5. We divide that 5 by 2.5 and we're going to get 2. And there is this other 2 and that gives us 4%. And that is how the answer becomes 4. Again, that one is as simple as that. And let's look at the last example, which is in the May-June 2005 question 4. And this is how it goes. In an experiment, a radio-controlled car takes 2.5 plus or minus 0.05 seconds. So absolute uncertainty is given. Travels a distance of this much, again with the absolute uncertainty. What is the car's average speed and the uncertainty in this value? What is the car's average speed? So how do we work out speed? Speed is worked out as distance covered divided by time. So the absolute uncertainty in speed divided by the speed itself is going to be equal to the absolute uncertainty in the distance divided by the distance plus the absolute uncertainty in time divided by time. So I think it is important here that, unlike in the previous question where we saw no need for calculating the power because we wanted the percentage uncertainty, here it is important to calculate the speed. 40, of course, divided by 2.5. 40 divided by 2.5 we get 16. 16. So how do we write this 16? Do we just leave it as 16, or do we write it as 16.0? How do we know what to write down? It is the absolute uncertainty that will tell us. It is this value that will tell us. So over here you'll have delta V over 16 is going to be equal to delta D, which is 0.1 over 40 plus 0.05 over 2.5. So it is a delta V which I'm interested in. So 0.1, you divide that by 40, you're going to get 0.0025, 0025 plus 0.05 divided by 2.5, 0.02, 0.02, all this multiplied by 16. So I have 0.0025 plus 0.02. I get 0.0225. Multiply that one by 16. I get 0.36. 0.36. You see, these are two significant figures. So I will write it to one significant figure, which is 0.4 meters per second. And it is the way this one is written that dictates how 16 should be written. And because it affects the first decimal of this number, I've got to write a V, and I will include 0.0 plus or minus 0.4. Everything meters per second. And that is why C is the correct answer. So you see how knowing how to write the number of significant figures in the absolute uncertainty dictates how we should write the value that we have just calculated. And those are some of the examples that I was able to get from these past papers. If you go to the video description, you will find that I've given more examples. I've given more examples in the various past papers. I've given you the past paper and the question that you need to look at that pertains to uncertainties. And indeed, in any past paper, you'll always get a question on uncertainties. One other feature that I have included in this video, and it applies to other videos that I have released of late, is that I've put timestamps so that should you want to go to where I'm talking about a particular example, just in this video, because I've covered like 5 examples. If you want to go to the first example or second example, even third example, quickly without wasting time, all you need to do is just hover the cursor over the scroll bar of the video and the various questions will pop up. And when the question of your choice pops up, just click on it and the video will just jump to that particular section and you can review it very, very quickly. That helps you to go through this type of video, especially when the video is very long. Otherwise, until next time, when I come up with another video teaching you concept in advanced level physics, it's goodbye.